All right, good afternoon, everybody. So the reading and homework assignments have not changed since last time. I still want you to look at Exercise 1 Guide on the D2L course webpage and Chapter 2 of the book. So you should have Chapter 2 and Chapter 1 of the book finished by Thursday. We've got exercises 1 to 3 due on Thursday, and also on Thursday, we want you to pick your partner for the first exercise, and we'll have a sign up for which dev kit you want to use for the semester. And as you know, some of the dev kits are limited. And by the 31st, which is a week from yesterday, or a Monday, we expect you to have the dev kits checked out so that you can complete exercise 1 by February 6th, which I think is also a Monday. Okay, so you, what? Before midnight. Before midnight. Okay, so you'll have a couple weeks to work on that. But exercise 1 is pretty lengthy, so you want to get started on it as soon as you can. It's split into 4 sections. The first couple of sections are more theoretical. You have to read a couple papers. You don't actually do any coding work until the 3rd section of it. So you want to get started on that part of it right away. Okay? And in particular, the Liu and Leyland paper is a pretty dense paper. It's fairly long, but it's not horribly long. But it does take a while to get through. So you really have to be concentrating. It's not something that you are going to read in an hour one day late at night. That's not going to work. Okay, so you're going to have to open that paper up early in the day and expect that it's going to take a few hours to get through it. But you've got a couple weeks to do that, so you want to get started with that fairly soon. Okay? Any questions about that? Okay, so next we have the placement exam, and as you know, the purpose of this is to help you. Okay, we're trying to find out if you have gaps in your background. We're setting up workshops right now to help people with those gaps. The first one will be on Friday, covering some basics of Linux. And unless you're a real expert in Linux, anybody in this class could benefit from that. So you're not required to attend it unless the results from the placement exam tell us that you need to attend it. Okay? But it's optional for everybody. If you want to go, you can. I don't have any details about where or when exactly on Friday it's going to be, but I do know that's going to be on Friday. There'll also be a workshop on digital logic design and another one on C programming that will happen the following week, or perhaps on the weekend. We haven't got that completely set up yet. So anyway, here's the placement exam. This is probably going to take you 20 minutes to a half an hour, I would guess. But remember, it's not for a grade. Okay, so just do your best and don't worry about it too much. If you don't know the answer, you don't have to mark anything. Okay, but that will tell us, kind of where, maybe you need some extra work. So there are 39 people enrolled in this class, and there's only spots for 30. Okay, so we still have a wait list and so on. But one thing that is true is that taking this placement exam is a requirement for continued enrollment in the class. And I don't think that all 39 people are here. So if you have some friends who are missing, who thought that, hey, they're doing an exam today, I don't need to come, they need to figure out and make arrangements with me to take this exam by tomorrow. if they want to stay in the course. Okay? So we're serious about having you do this because we want to make sure that people are prepared before they get working on things. So let your friends know who aren't here today that are enrolled in this class. They need to talk to me. Okay? Unless, of course, they show up in the next 5 minutes. There we go. You want one of those? Three, 4, 5. I think it's 5. All right. 1, 2, 3, 4. 1, 2. And so for the distance students, there'll be a version of this exam out on D2L. Later on, you need to email me to set up a time when you can take the placement exam. And with that, Karthik, you can probably stop the recording for about the next half hour or so. All right, thanks. You get all semester, right? At least I hope so. So we want to continue to talk more about real-time embedded systems here. And but before I do that, before I get going into this, I want to introduce our grader. Raul, you want to come up and introduce yourself? And so he's going to grade everything, so be nice to him.
Hello class, so this is Rahul. I'll be grading your assignments and homework for this semester, and you can approach anytime through email or I'll be holding office hours. The person will be telling you. You can come and meet me at that time.
All right, thanks. Question?
We'll be telling you in a short duration.
All right. So there you go. So, this is a picture of an example of a real-time embedded system. And I know it looks kind of unusual, but it was put together specifically to try to create many, many different software services that all had real-time deadlines to see what happened when you put together everything that could possibly be a load or create a problem for a real-time system all together in one place and make it work. And so this is actually Dr. Sievert's test platform for part of his PhD dissertation. It has multiple software services, and they are reconfigurable. It has synchronization between services and communication between services, multiple sensor inputs and actuator output interfaces. It includes intermediate I/O, shared memory, messaging. So there's all sorts of things going on here. It made it about as complex as you can make it and got everything to work and made some measurements of performance. And so this is a diagram that tries to show a picture of the relationships between all the different components of this embedded system. And it's split into different sections, but also considers the impact of time as well. So not only is it a block diagram, but it's also kind of a timing diagram all put together in one. So you have a separation here between software and hardware. So the hardware down here is a NTSC decoder, so this is a camera, if you will. There's some serial outputs that are used for control of motors and camera positioning, and also what he's got thrust here for. This is basically a little drone on rails kind of a thing. And then there's also an Ethernet connection. So all three of these things are going to have real-time requirements. They need to be serviced real-time. The camera is going to update with frames at 30 hertz, so every 30th of a second or so, you're going to get a frame ready. You've got a software function here that is going to work with the video, create an RGB buffer here, and there's also going to be information directly coming from the hardware into this buffer, and so on. And then in a lesser frequency, you'll have some frame display devices, software components, and also a navigation component, which is then going to control the camera and the thrust and some timing as well. You'll have a grayscale buffer in the middle of here, which is going to package up this video information and send it to a remote display via the Ethernet. Okay, so not only do you have local video control, but you also have remote control via the Ethernet done with this device. And as you can see, the most frequent components are on the left. The less frequent components are on the right. Okay, so in terms of time, you kind of have a priority based on going from left to right. If you're going to use rate monotonic scheduling policy, which one of these components in the software frame here would run first? Anybody? Yeah, 30 hertz. So that has the shortest period. It's the most frequent. So the policy is that the highest priority is given to those components with, or those tasks with the shortest period, right? So this has the shortest period, so it would tend to run first in rate monotonic, right? So he tried, I'm sure, several different kind of policies with this compared to performance. So why use software for hard real-time systems? What's your alternative? Can you build a real-time system without software?
ASICs.
ASICs, right. So you could do everything in hardware, right? In particular, you could have an ASIC or an FPGA state machine solution with hardware clock deterministic solutions. Always works. You don't have to worry about priority inversion. You don't have to worry about any of the kind of problems that we're going to study a little bit more in real time. So why would you build a system based on software that was going to be real time then? Why not just do it this way with state machines? What's that?
Cheaper.
Cheaper?
The software is more configurable.
Software is small and configurable. Hardware is going to tend to get big, particularly as that state machine has more and more states. It's going to get more and more complicated, require a bigger ASIC or a bigger FPGA. These are expensive devices compared to a small microprocessor or something like that. So another nice thing about hardware is you can now update it with new bit streams. So the advantage of it being upgradable has kind of gone away. You can have upgradable hardware as well as software. Okay, still looking at hardware. Software, though, is still a little simpler for field upgrade. So it's reconfigurable at runtime. It's a little more flexible. It's a little easier to put out a software patch than it is to put out a hardware patch. In either case, if your patch doesn't work, hopefully it can be detected and it'll revert back to whatever the previous version is. But with software, all that requires is some extra program memory. With hardware, now you have to have extra configuration memory, and configuration memory is going to be more expensive typically. Okay? FPGAs are more costly per unit, so that's the main reason. Another thing that's been used as a reason in the past is the cost of software engineering versus hardware engineering. So, is it cheaper to hire software engineers or hardware engineers?
Software.
I should have made that into a clicker question. Software or hardware? The answer is it depends on what expertise you're trying to get, but typically FPGA designers are pretty expensive. They're few and far between. They're harder to find, and particularly it's hard to find people that are very productive at that. So they usually get somewhat of a premium in price versus software engineers. So if you can do the work in software instead of hardware, it might be a little cheaper for you as far as NRE is concerned. Okay? But in general, the implementations in software are going to be less expensive. That's the big motivation for doing it in real-time systems. If you get into a jam, though, you can kind of keep this in the back of your mind. Hey, we're just not able to make this processor run fast enough to meet the real-time deadlines. You can put it in FPGA and have some of the work, at least, be done in hardware. And then you shouldn't have a problem with a real-time deadline in that case. Okay? So now here is a clicker question. All right. So in this room, base frequency code is CA, so you have to hold the power button down for a couple seconds until the light blinks, and then press C and A, and then you should get a green light that tells you that you're connected to the base station here and are able to put in your answer. So the question is, what is an RTOS? Answer A is a software-based task scheduler. Answer B is a collection of software that controls a real-time system. C is an operating system that responds to requests with a short and predictable delay and processes data in deterministic cycles. D is a software system driven by external events for which services provide a response before a deadline relative to the request. And E is an operating system intended to serve real-time application process data as it comes in, typically without buffering delays. So which one of these is the best definition of an RTOS? A, B, C, D, or E? Go ahead and pick on your clicker. I got 8, 11, 12, 13. Is it not recording?
What happens if I click multiple times?
If you click multiple times, then if you just keep clicking A, it'll only register A once. If you click A and then you click C, it's going to throw the A out. And whatever you click last is what it's going to pick. That's not good.
I don't know if it's working also.
So you can change your mind, as people know. Right? Okay. So
There is no background signal for that.
I don't know.
So the class believes that the answer is D. Oh. Or C. Okay. So it turns out these are all definitions that I've been able to find of an RTOS from various sources. But D is actually the closest to the definition in the book. And so this is the one that we'll like the most by the end of the semester, right? Okay. There's something good about each one of these things, but I think D is probably the most accurate and complete definition of what an RTOS is. Okay. Stop. Okay. All right. The book does not give you an awful lot of background in RTOSs. It just kind of jumps right in there and starts talking about real-time processes and everything like that. And what I kind of discovered the last time I taught this course was that people got a little confused by that, and so I'm going to go through a little bit of an overview of operating systems, what they are, how they came to be, and so on, to give you some background and some context for the reading that you're going to do in the book, and so for some of the concepts that you'll kind of know what everything is based on. So an operating system is some software that provides the interface between user applications and computer hardware. And in particular, it abstracts the hardware so that people writing user applications don't need to know very much about hardware. This is particularly important because people that write user applications a lot of times aren't very bright. Okay? The smart people write embedded code, right? They leave the easier stuff to user applications. So there's a number of OSs on the market for various hardware platforms. You have Windows, Linux, Unix, Mac OS, Android, so on. The general idea is all the hardware is down here, the user applications up here, and you have the operating system in the middle. And the OS a lot of times will include some kind of a shell with commands and a kernel, which is kind of the core of the operating system. All right? And there'll be drivers. The drivers may be external to the operating system, or they may be part of the operating system, depending on what kind of an operating system it is. So here are some functions of an operating system: managing the processor, the memory, the devices, file systems, system security, fault tolerance and error detection, multitasking and job accounting, and task coordination. And this last thing is the thing that's most important when we're working with real-time operating systems. We're worried about how much time does each task take, and allowing each task to have a certain amount of time, because time is being used as a precious resource. So there's lots of different types of operating systems. A single user OS, where you might have multiple programs with only one user access. A typical example of this would be a PC, particularly an older PC. Newer ones might allow multi-users. The multi-user OS was typical back in the days when computers were really large systems and lots of different people wanted to use the same computer because not everybody could have one. And they used batch operating systems typically. So all your jobs are submitted as batches. And so they'd run a batch of jobs. They prepare all the output and put that in bins, and people would come by and pick it up later because nobody expected to get an answer from the computer right away. And the idea behind all of this is that you're trying to maximize processor usage. So you're not worried so much about user applications, but you have CPU time. That's the most valuable thing, and so that's the thing that you're managing. There's still some OSs like this for particular kinds of machines in different places. Particularly when you have supercomputers, you still have this situation. Okay. A time-sharing OS is used when the processor's time is going to be shared upon multiple users. A typical application might be some mini computer that had lots of video screens and video terminals tied to it. And so you have multiple people using the same CPU, but they're all using a different user interface. And so then you would have user applications in that kind of situation. The distributed OS happens when you have multiple CPUs and one OS. And its assumption is the processors are interconnected with some high-speed kind of connection. And we even see that now with modern processors that have multiple cores inside the same device. You have more than one CPU. The OS has got to be a little more sophisticated in that case. So an embedded operating system is designed to be used in embedded computer systems with limited resources. There are other objectives other than maximizing CPU usage like there has been prior to this. Energy efficiency is a big objective, so we might actually turn the CPU off for a while in an embedded OS. So, if it's embedded, does it mean it's real time? Yes or no?
May not be.
May not be. Okay, so you can have embedded systems that are not necessarily real time. And you can have real time systems that are not necessarily embedded, but the two do tend to go together. But we don't want to confuse them and think that they're the same, because they do represent something slightly different. So a real time OS, multitasking OS targeted at real time applications with real time constraints, has to respond quickly to events. So it's the response time that matters in a real-time system. You have to respond before a deadline. Otherwise, something bad might happen. It says that it's multitasking. Why can't you have a real-time operating system that is single-tasking? If it's single-tasking, does that mean it's not real-time?
Why do you need an OS for a single task?
Why do you need an OS for single-tasking? If it only does one thing, right? It might not even be an OS. It might just be a cyclic executive. It's just one program. You're not going to switch tasks ever. You're never going to do anything different. Then, yeah, you don't really need an OS in a single-tasking kind of situation. The idea here is you've got two tasks. At least one of them's got some kind of real-time deadline. You may be doing one task, you're going to have to switch to the other task in order to meet the deadline. Okay, so operating system services, scheduling tasks, particularly in real time, that's the really important one. Other things it needs to do, though, are allocating memory resources, managing IOs, managing file systems, networking, detecting and fixing errors, protecting and securing information. Okay. So how do some of these other services affect real-time performance, and how might they interfere with real-time deadlines being met?
Overhead.
What's that?
Overhead.
Overhead? Yep, overhead. So you have to be careful to still do some of these things, because if you don't, in other words, if you have a lot of real-time going on, you have a real-time process that's hogging the processor such that memory doesn't get allocated, you might get into a situation where that real-time process runs out of memory. Okay? And so you do have to be careful about making sure that all the services are still going to be managed, but of course managing the services is going to take time, which is going to take some time away from real-time. You have to plan for that ahead of time. You have to model the time that some of these other things take when you're working with a real-time system. And we'll see that more. We'll get into a chapter about I/O and how I/O can be the constraining factor on real-time performance. Okay. So how did operating systems come into existence? So the very first computers didn't have operating systems. Okay, you transfer programs by using switches, believe it or not. So you had a list of switches that identified the address, and another list of switches that identified the data. You set all the switches to a certain address. You set the data to a certain number, and then you hit a load button, and it will load that data into that address of memory. And then you kept doing that until you had a whole program in, and then you would push a button that would make it run the program. No operating system. Okay? You had an operator, but you didn't have an operating system. And so, scheduling tool, sign-up sheets. If you wanted to run a program, you had to sign up a sheet, and then you got some time to come in and load your program and run it. This sounds really old, I know, but I actually had a computer lab when I was in college where we had to do this. Where we were working with inexpensive mini computers that had this kind of an interface on them. I think it was the last year that they were doing that, though. After that, they went to video terminal machines. But anyway, so then after that, you had lots of people who wanted to use the computer at the same time. You had an operator. You punched cards for programs. You had a big deck like this. It would be fed into the computer through a card reader, and the operator would handle the task of putting all those cards into the computer, and then the result would be some kind of printout, typically, and they would put the printout in your bin, and then you go pick it up later. This was really lots of fun. You know, it's something you guys have all missed out on, getting the chance to punch cards. And I used to have programs that were so long that when they were fed in, usually it would chew up one of the cards in the reader, so I'd have to punch that card again, so they'd have to read the whole deck in again. And by then, because of the humidity in the area, another one of the cards would be unreadable, and so sometimes it would take me 4 or 5 times. So if you think you're frustrated with your computer now, believe me, everything is easy now. So it's good that we don't have to continue to do that sort of thing. So then they had batch systems, so they'd run a batch of jobs without user interaction. Problematic. Yeah, it was kind of problematic. Things tended to get mixed up. Sometimes they put your output in somebody else's bin and it would take forever to find it. Some things like that still happen, but much less so. So then people started to do multi-programming, where you have more than one program running on the CPU at a time. So the idea is you're going to be switched between programs. If a program gets blocked because it needs some other kind of information, then you switch over and run another program. You want the CPU to be busy all the time because the CPUs cost millions of dollars, they're very expensive. So this first started to be used with a Burroughs machine and an IBM System 360, which actually was the first computer that I worked on years ago. Then they developed time-sharing systems where, again, you have interactive terminals and time slices for users. And then finally, based on these time-sharing systems, they developed OSs for smaller machines like personal computers. One of the first time-sharing systems was Unix. So Unix was a time-sharing system. Linux is based on Unix, right? So there's a history there. And when you get confused about why Linux does certain things a certain way, it's because it's based on Unix, and the Unix machine was trying to handle a whole bunch of users at the same time that were all using video terminals to try to access the computer. So some of that hopefully will make sense when you see that. So putting an OS together is fairly challenging. It's a challenging software engineering problem. You have these issues when you're trying to design an OS. We're not going to talk about comparisons of OSs so much here, but just know that this is something that people who are trying to design OSs care about. Backwards compatibility in particular has had a lot of influence on what Windows has become, because they've tried to make things backwards compatible to some extent. So there are different types of OS. The traditional OS structure is monolithic. We have a single program that has all the kernel code and offers all the OS services. So you have system calls here from external processes. These kinds of systems are less portable, difficult to maintain. You have a minor bug will crash the entire thing. It is faster, though, so it has some performance advantages. But maintenance-wise, it's a little more difficult to deal with. Reliability-wise, it's sometimes a little more difficult to deal with. Unix and Unix-like OSs, including Linux, are monolithic in structure. The device driver is part of the operating system. It's built into the kernel. Okay? It's not separate like it might be in other things. So if you have a microkernel, the idea is to simplify the kernel design and have privileged spaces to kind of separate out certain services. The advantages of this is that you have better isolation of software. You can do unit testing. You have more rapid development typically with this. And so here you have a kernel which is much smaller. It has the scheduler. It has some basic memory. But now device drivers are outside of the kernel. They're still in the privileged space. So the unprivileged space has all the user apps in it. Privileged space has got drivers, servers, and then the kernel itself. Okay? But the kernel is much smaller. Now if you have a bad driver, it's not going to break the kernel. The kernel can still keep running And it can actually shut off this external device so that it gives you better reliability for an embedded system. Okay? Problem with this approach is you end up using more memory. You have more frequent context switching, inter-process communication. I had a friend who used to call it the march of the messages, where you have lots of inter-messaging going on between the drivers and the kernel, and that stuff is going all the time. So not so easy to implement, so the design of these kinds of systems are a little more difficult. Anybody know an example of a microkernel type of an operating system? Okay. QNX is one example, and because of the microkernel and the reliability that you get from it, these things tend to be somewhat bulletproof. That's become kind of the standard for use in the automobile industry, because embedded systems in automobiles are working in a particularly harsh environment. It's really nasty. You have all the ignition noise, you have wide temperature ranges, all that kind of stuff. So it's reliability challenged, and so they are using QNX with this kind of a structure. So in general, monolithic gives you better performance, but microkernels have better modularity, extensibility, reliability. Most modern OSs are going to be somewhat of a combination of these. They're going to try to keep the kernel small, but servers are going to be within the kernel space still. So they give you a couple of examples here. So then if you have an embedded OS, you're worried now more about predictability and determinism, especially if it's real time. So within real time, the thing that really sorts that out and really identifies it is the unified understanding of the deadline. So real-time operating systems have to meet a deadline. And you'll probably hear this over and over again. So you go through the course and you'll start saying it yourself because it's true. Real-time means deadlines. So you have to meet the deadlines. So they're designed to be fast. Everything sits on the real-time kernel, even the device driver. I'm not sure that's always true. So what might not be important that's not real-time? So the GUI a lot of times is not real-time necessarily, or it's soft real-time. Security may not be real-time depending on the application. But then everything else is going to be run by the real-time system. So you don't necessarily need an RTOS in an embedded system. You can use a Superloop, right? And the Superloop is actually probably still the most common type of a system that's used in embedded systems. The last survey I saw said people are still mostly rolling their own instead of writing RTOSs. So there's pluses and minuses to doing that. Superloops are straightforward. They fit within the computational model of embedded systems. They're dependent on use of interrupt service routines, though. It says that they have to be lengthy. That's not always true. I would disagree with that. This is ARM's viewpoint, but you can build superloops where the interrupts are short, and some of the processing is done in the main loop instead. But typically, they tend to be set up so that for every event that happens that has an interrupt, that event is completely handled by the interrupt service handler. Okay? What that does is it causes problems in terms of real-time performance because now you have a delay. If you have some device that's particularly complicated that requires lots and lots of servicing time and processing, the handler gets to be so long that by the time it returns, other real-time deadlines might have been missed. Okay, so when you design this kind of system, you have to be very careful about that. And you almost have to have some understanding of worst-case execution times, build that into your model, have a big system timing diagram so that you make sure that you don't miss any real-time deadlines. The biggest problem with the Superloop, though, is that any change of interrupt service routines, or when you add extra real-time events that have to be tied to an interrupt, any changes like that ripple throughout the entire system. So the Superloop is not very well isolated. Changes in one place can affect changes in another. It can be a real headache to try to debug problems that come up that are associated with real-time with this. So your alternative then is to use an operating system which encapsulates tasks. And then you get scheduling based on demand, not based on where are you in the loop as you're going around or whether or not an interrupt occurs. So you have more control then over what happens, at least in theory. Interrupt service routines are short. Most of the processing is going to be done within the operating system. It gives you multitasking, or at least the illusion of multitasking, better communication, better resource management, lots of other services that come from using a commercial RTOS in particular, although there are open source RTOSs available now too, free RTOS being an example of that, where you get all those services for free. When you're trying to do something here, every time you have to add another service, it's a lot of additional code. And this can even be true within commercial operating systems. So we used to use VxWorks in this class. The last time they decided to start using a new camera with the class, Professor Seward had to write a new driver for the camera in VxWorks. It required him to put together 4,000 lines of code. And what he discovered was if he had done it in Linux, the driver is already written by someone else, so he didn't have to do anything. Okay, so when you're doing a Superloop, if you want to add anything, it means lots and lots of extra software work. And that might even be true in some operating systems that you might buy or use. But when you use something like Linux, which has such a huge open source community and so many drivers are already available and used, it's more likely that if you want to add a device, the driver already exists. And that's a really nice aspect of those operating systems. Is one of the things that's driven lots of people to use Linux and want to try to use Linux, even in real-time situations where maybe it wasn't designed for that, because it has all these other advantages, and that's, even in this course, that's one of the things that has happened, I think. Okay. Any questions so far about any of this? Okay, we're going through it pretty quick, but I think most of you probably know most of this, I would guess. Okay. Real-time operating system is an OS that serves real-time applications, has short and predictable delay, and processes data in deterministic cycles. So you can see where one of those RTOS definitions came from here. So a lot of people get confused and they think the basic criteria and objective of real-time operating systems is to be fast. That is not what they're trying to do. Okay? They're not trying to be fast. They're trying to be deterministic, okay, and responsive. Those are different than being fast. Now, it's true if you're fast, you can be somewhat responsive as long as you are able to respond when the event comes that needs to be responded to. But that by itself, being fast, is not enough to meet real-time deadlines. And certainly you can have Linux systems that are really fast that don't meet real-time deadlines because they get stuck doing something else. They get tied up with a driver that won't let go of the processor, and things like that will happen. So in particular, real-time operating systems have to be nimble. So they're aimed at being deterministic and responsive rather than having high throughput. So your performance measurement is different then. It's not, how many cycles per second can you run through instructions in the operating system, or how fast can it execute some kind of a benchmark algorithm. The performance measured by jitter, the variability of time it takes to complete a task. So if you have a soft real-time operating system, you might have more jitter, but more generally you're going to meet a deadline. If you have hard real-time operating system, you have less jitter. Jitter is usually going to be measured in microseconds or even less in order to be able to meet the deadlines deterministically. In other words, you have to meet the deadline every single time. You can't have a lot of variation in how much time it takes the software to run certain tasks. Okay. So there's two common designs for operating systems. So you can have event-driven real-time operating systems that are preemptive, and they have a notion of priority, so the higher priority stuff is going to get served first. You can also have time-sharing real-time operating systems, which are non-preemptive, so you have some kind of task scheduler that does like round-robin kind of scheduling, where it tries to give a little bit of time to everybody. And it does this every time around a loop, sort of. That doesn't mean it's a super loop, okay, but it has got a scheduler that is going to give a little bit of time to every task. Sometimes some tasks are going to get time several times before another one will if they have a little higher priority. That's kind of how everything gets divided up. The problem with time-sharing operating systems is you have a lot of extra task switching, so they're not as efficient in using CPU resource as an event-driven, preemptive type of operating system would be. So most of your real-time operating systems, at least the commercial ones that are available, tend to be preemptive, event-driven types of operating systems. So they use this first philosophy. Which philosophy does Linux use? Is it event-driven, preemptive, or is it a time-sharing type? Yeah, so your desktop Linux, so Ubuntu is going to be a time-sharing type. It's going to try to be fair to everybody. And that's part of the Linux philosophy, too, overall. It's philosophy of computing. That fairness gets in there. But, as a consequence, it's not so good then at meeting real-time deadlines, and that's why you have the real-time extensions, the real-time patch, which allows you to introduce some preemption into this time-sharing type of an operating system. Okay, so now it's going to be a little confusing because you're going to have both, but we'll work through that. So in a typical RTOS, we showed you some diagrams of this where you usually have three kinds of states: running, ready, or blocked. You might have another one that's called delayed, another one called suspended in the model that we used. So the idea behind task scheduling is you can only run one task at a time. And so there's different kinds of scheduling algorithms that exist. You can have cooperative scheduling where you don't have preemption. You're assuming the tasks are going to end themselves in a cooperative manner. Unless, of course, you end up with a driver that never comes back, kind of a problem. Those happen. If you're preemptive, then you don't have to worry about that problem because tasks can be interrupted by other tasks of higher priorities. The earliest deadline first approach, the task with the earliest deadline is served first, so it's not doing a round-robin kind of cooperative scheduling, but in fact is looking as a task ends. It looks at the tasks that are ready to run and picks out the one that has the earliest deadline. Oh, looks like we have another deadline. Okay. So, and then there's a list of some examples of real-time operating systems. Okay, so we're going to go through talking about scheduling and scheduling algorithms a little more now in some detail, and that's also gone over in the book in chapters 2 and chapter 3. I'll talk about scheduling somewhat. We'll talk about RTOS schedulers and the POSIX real-time extensions for Linux. We'll also talk about free RTOS and make allusions to VxWorks occasionally. How to define what real-time services are. Linux thread analysis and debug when you use schedule FIFO type of a scheduling algorithm, how you establish synchronization, and issues that come from having a fair operating system versus an unfair RTOS. So, fair versus unfair scheduling. So, the CFS, or completely fair scheduler in Linux, is fair. Everyone gets a slice of the pie. Some get slices more often than others. But everybody always gets their slice of pie. And so this is the default scheduler within Linux. So this is what runs unless you go in and make it do something different. Now, the nice thing about it, it is somewhat configurable. You can go in and change what the scheduling algorithm is. This particular scheduler, though, requires that you have a programmable interval timer. So you'll see references to some of the exercise documents about a PIT. This is what we're talking about in that case. And the idea is that this timer is going to raise time-based interrupts. It gives you the concept of a quantum. So scheduling changes can mean at each quantum tick. So there's a timer tick that runs everything. And every time that timer runs out, then the scheduler gets to run, and it gets to decide which task gets to run at this particular point in time. Okay? And this particular schedule is going to make sure that all tasks, all threads, get to make progress all the time, so nobody ever gets starved and doesn't have any CPU resource. Everybody gets a little bit. But this does not provide any kind of guarantee toward any kind of predictable response. So if you have a real-time deadline, you have a real-time task, this scheduler is not going to give it priority given that the deadline is coming up. It's going to continue to run its algorithm and give everybody their fair slice of things. And so that's why Linux can't give you any real guarantees for anything. So if you instead used a priority preemptive run to completion RTOS, things are going to be unfair. Okay, so you have to get used to that. So any task is going to run at priority until it completes and exits, in which case it's going to give up the processor at that point, or until it yields, sleeps, or a higher priority test. You can also block on a secondary resource or system call, or an interrupt gets raised. That can stop the task from running as well. And so, you have a situation here where the scheduler is going to have to be more complex and more sophisticated and deal with the notion of priorities and so on, and know kind of what's running every time it gets the opportunity to run and make some decisions about what task should be running now, and know that external changes in the system can make it so that priorities are going to change, and so one task is now going to get blocked and another task is going to run. Okay. Any questions about any of this so far? Okay. We'll keep talking about this next time and get into a little more details of scheduling, and may get to the point where we can introduce Cheddar and how you use Cheddar to create timing diagrams of operating systems based on their scheduling algorithm. Okay, so that should be good. So we will see you on Thursday. Be sure to let your friends know if they haven't finished the exam. You need to come and do that.
I'm not sure you did.
You didn't say it.
A while.
अच्छा है। डाउनलोड कर